Welcome back to the third and final episode of our look at the game Cuboid and its use of arrowized functional reactive programming and OpenGL. And now it's time to actually deconstruct the source code. Let's start by taking a look at main.hs. And it turns out that we've seen everything in here. There's not that much to begin with. But we've seen it all because we took it and used it in our bouncing ball program. The only parts we haven't seen are the ones that were commented out in our main here. And that was having to do with the input. And really it boils down to two lines here. One is a keyboard and mouse callback from OpenGL that writes the event out into the new input IO ref. And the second is, well, it's two lines, but one reads that input out and then passes it to React. Our React callback right now is main SF, which was only dealing with time. But in Cuboid, the input's passed in and it's used in parse input. So that's the next place for us to go, is input.hs. So let's take a look at parse input, and it should be familiar, at least the arrow notation that's used here. The first thing it does is take an input event, which we might as well take a look at the type of here, which is a record that shows the key, the state it's in, and any modifiers that were pressed. And the first thing it does is only pulls out the key down events, filtering for keys that have been pushed down, and presumably repeats when the key is held down, and then names that down. Next, the following arrows, these 8 here, count from that list of key down events. Each of these 8 keys, WASD, which you'll be familiar with if you've played first-person shooter games on the PC, and up, down, right, and left arrow keys. Finally, it returns a parsed input, which is also here in types. That is a record that shows the respective keys that were read. W, A, S, and D are returned as doubles, or as counts, while up, down, left, and right are returned as input events. And we'll see the reason for this, but you can think of it as W, A, S, and D are doing rotation, which is purely a transformation used for display. It's not something that's going to change the state of the game. Whereas the up, down, left, and right arrow keys actually cause the player ball to move, and presumably are used by the signal functions to change the state of the game. So I'm going to skip over count key and filter key because they're similar to other arrows we've seen. Briefly point out that key integral is using this integral that we were using in our bouncing ball that should give you some sort of intuition on what it's doing with the count key here, which again is only used for W, A, S, and D. So switching back to main, the next thing to look at is update here. But first let's take a look at draw, because we've covered most of this as well in graphics.hs. In fact, we copied out almost everything into our main here and commented out some parts, such as doing the rotation of the cube, rendering the cube itself as a wireframe, rendering the goal, and rendering the obstacles, which really aren't that much more complicated than rendering the player shape that we've done, except for these vector and matrix transformations, which are really out of the scope of this episode. So that's it for graphics. And now there's update here. And this is something we haven't seen yet, which is the heart of the game, Cuboid. There's only 3 functions inside of it: integral prime, which is commented here as snapping integral, update, and select speed. Let's skip over integral prime for a moment and take a look at update. Even though this function fits on a single screen, it can be a little bit intimidating to look at first. One thing that you can do is create a diagram to show what's going on with these arrows. And I made a rough one here. It's not perfectly complete or accurate, but it should give you some idea of what's happening with these main 6 arrows here. And while the diagram might give you a feel for what's happening, for me to understand it, I like to read through these arrows one by one. Now, something that you may have noticed from the diagram, and that I'm going to point out here, maybe a little bit strange. Notice that win-lose here is used as an input for this arrow, and it's collected from this arrow above, which isn't too surprising. But if you look up 2 lines, you'll see that win-lose is being passed in to this arrow above it. Now, in pure code, it may not be surprising to see named values used on a line above where they're defined. But in a monad block or an arrow block, which looks very similar, it might be. And the reason that the code can do this is it's using this rec or recursive keyword here. This is what allows the diagram to have arrows going everywhere. Values are being used in one place to produce a value that may actually then be used to produce the value itself, which seems like a bit of a paradox. If we look at win-lose again, it uses position, or pos, which uses position I, which uses win-lose, so there's a cycle here. But Yampa knows what to do with this, and in some cases you may need to use a delay if you need to straighten out the sequencing. Let's take a look at a couple of these helper functions here. Calculate player position is a pure function that takes the position that we've calculated and the level, and this operator here is vector addition. You'll also see vector subtraction, vector multiplication. And it simply adds the position vector or the movement of the player on this level to the starting point in the level. Test bounds here checks to see if a position is outside of a cube of the given size by checking its x, y, and z components. And test bounds is used in test win-lose condition here. Once the ball or the player ball has moved outside of the bounds of the level, that is a loss. Whereas if the distance between the position and the endpoint of the level is less than a certain amount, it's considered a collision, or a collision between the player ball and the goal, and a win is generated. And in any other case, there's no event and the game continues. To see what count hold is doing, let's see where it's used here in determining the level. It takes the wins, counts them, turns that into an integer, and then uses that integer to index the levels list, which makes sense. And finally, what's returned here is a record with just 3 elements. And if we look at it, it actually contains everything that the game needs to render the state of it to the screen. It has the position that the player should be rendered at, or the red sphere. It has an X rotation, which is used to determine which angle to render the wireframe cube, or the level, or bounds of the level. And you'll notice that only W count and S count are used here. Presumably A and D was used in the past to change the Y rotation, but was removed for some reason, and traces of it is still in the game. And finally, it returns the level, which gives the positions to render the goal and obstacles at. One other interesting thing to notice is that while we might think of the game as being discrete in terms of levels, where level 1 is loaded and then some action happens, and once level 1 is finished, it is deconstructed, thrown out, deleted, something like that, and level 2 is loaded, and all the variables are set up again and put into motion. But for Cuboid, the game is one continuous function, and the levels are changed just through this held count here of the number of win events above. Now let's take a look at select speed. Actually, I'm not going to go into it in too much detail because it's mostly vector arithmetic and some fiddly magic numbers. But fortunately, nothing in it is really new. If you've understood update, you should be able to figure out select speed. So finally, there is integral prime, which the comment says is a snapping integral. Now, if you really wanted to understand what's going on, you could go down the rabbit hole and begin looking at what scan and ipre and some of these other primitive Yampa signal function or arrows do. But I think it might be easier to get an idea of what's going on by just replacing the use of integral prime with integral. So we can do that here and here. And let's see if it's used anywhere else. Oh, that's it. So let's recompile this. And run it again. And so now you can see that when we move the ball, it's not precisely lined up anymore. The game is still working, but notice how the ball is sort of on an edge here. And it just went through that other cube. Let's see if we can see that one more time. So you can guess at this point that a snapping integral allows us to be precise where the movement of the player sphere ends, even though we are getting called in the React loop at unpredictable moments in time by OpenGL, or the OpenGL idle callback. And believe it or not, with that we've seen the entire game. We've looked at graphics.hs, input.hs, main.hs, set up as part of Cabal. We've looked through types at, I believe, all the types here. We've looked through update just now, and utils is some vector calculation code. But even though we've seen all the code, to wrap up without actually making some changes would be kind of boring. And I noticed a couple of things about the game that I'd like to change, which I think would make it better. The first, if you'll remember, is that the obstacles and the goal are rendered in the same color. And I'd like to have the goal stand out a little bit more. It is a sphere instead of a cube, but why don't we render the obstacles as blue, for example? So let's first go define the color blue here. And this is an OpenGL color, which is an RGB and then alpha value. And we can kind of guess at what these values should be here based on the other colors. So we'll make it looks something like this, and if it's not perfect, we can change it. And now, instead of using the color green to render an obstacle, we'll just use blue. So this should be a pretty straightforward change. Let's see how it looks. Well, it turned out a little bit more purple than I expected, and that's probably just because I have a little bit too much red in there and not as much green. Oh, there we go, that looks nice. But that's a pretty straightforward, simple change. What I'd really like to change is the controls. Notice that I have to do a lot of rotation because we only have 4 arrow movement keys, and in 3D space we need to move in 6 directions. So let's look back at the code in input, or rather in update. Under calculate speed, select speed, which I said we wouldn't cover, but there's one thing to look at here, and that is that the up and down keys are used for movement on the z-axis, and the left and right keys on the x-axis. So why don't we add some new keys for movement on the y-axis? And we can just try copying the code here. I'm going to use the comma and period keys. Comma, period. And we'll change z-axis to y-axis, which is defined right here, even though it's not being used currently. And we'll also need to update the input. So let's see if we can figure out or just guess how to do this. We'll filter key. Looking at count key, it looks like char is being used. So let's try that. Let's do comma first. So I wrote it that way. Char for the period events. And I'm not going to clean up the formatting just yet. We're also going to need comma events here and period events, which means we're going to need to change types to include that. So comma here, period here. And let's see how far that's gotten us. Well, it compiled correctly on the first try. Let's see if we can actually use it. So now, pressing the right key sends me off to the right as I'd expect. Down and up are on the z-axis. So if I press the correct key, I should be able to move up without rotating the cube. And that was the period key, and it worked. So now we can actually complete levels without rotating the cube at all due to better input. And now if you want to challenge for yourself, see if you can figure out how to rotate the cube in the other direction and what challenges that entails. And maybe you'll see why that was removed from the game. Or maybe it was just removed for simplicity. Or if you enjoyed the game and want to contribute, I'm sure that you could create some new levels for it. They're pretty simple list structure. And that's all I have for this episode. This marks the 11th episode of Code Deconstructed, and it's the 5th program that we've deconstructed. I've received overwhelmingly positive feedback, and I want to continue deconstructing programs with you. The latest 3 episodes were made possible by a suggestion to cover some functional reactive programming. And I really appreciate the suggestions and could do with some more to see what it is you're interested in learning about. But I've also received some requests to do some more basic tutorial videos of some simpler concepts in isolation. And I've also had an itch to not just deconstruct code on video, but do some programming from scratch as well, most likely in Haskell. So if you have some suggestions on a program you'd like to see built from scratch, leave me a comment and I'll take it into consideration. I have a couple ideas in mind. One is an implementation of Redo, which is a build system conceived by DJB. Another idea is to build a simple web application. So to reiterate, I'm going to continue making Code Deconstructed videos, although they probably won't come out with the same frequency, in order to make room for these other videos I'd like to make. Anyways, as always, thanks for watching, and I'll see you next time.